All right, new unit, new concepts. You already completed the exploration, which kind of introduced you to exponential functions as opposed to quadratic functions. So let's take a look at an example here. So our essential question is what are discrete exponential functions and how can you represent them? Okay, the discrete part is a review, which we'll briefly talk about. The main focus is exponential functions. So let's take a look at these two colleges and look at how much their prices grew over the years. So here's College A. They started out at 10,000. In year one, they went up to 11,000, and then they went up to 12,000, and they went up to 13,000. What's the pattern here? Well, they went up by 1,000 every year, right? Pretty clear pattern. College B, however, is not quite as obvious. What's going on here? 10,000, 11,000, 12,100, 13,310. Well, if we look at the pattern, that one went up by 1,000, and that one went up by 1,100, and that one went up by 1,210. And you can kind of see that these connect, right? This one is 10% of that one. This one is 10% of that one. So it went up by 10% each time. Or to put it another way, we took this number and we multiplied it by 1.1. So 110% each time. So that's another way to say it, is we multiplied it by 1.1. And this is actually the better way for the exponential functions. All right. So I'll let you pause and read this part, and then we'll talk about it briefly. Okay, so just to remember, discrete function, all that means is that we have specific points, right? That you can't buy half a ticket. You can't buy 2 1/3 ticket. So that's what makes it discrete. And then you see also when we graph it, we have those discrete points. We don't have lines and we don't have connected curves. Okay. To go back here for 1 second, how are the domains related? Well, the domains are the same, right? The domain here is the exact same as the domain here. And yet the graphs look very, very different. What's going on? Well, this one is just going up by 10 each time. But this one is being multiplied each time. This one is an exponential function because it's being doubled each time. Is the number of attendees. So this is the cost of tickets. You don't have to pay more the more tickets you get. However, their attendees are going up each time. So that's why that one's different. What you need to know from here, a little bit as a preview, is the constant ratio is 2. What we're multiplying by each time, we call that the constant ratio, because notice this hasn't changed. And that happens to be 2. What are we multiplying each time? And to find this, we can always divide 1 by what came before it. If we divided by 6 by 3, we would say, we doubled it. That's our constant ratio. Okay. So the limitations on the domains of these, well, they're both whole numbers. We can't have a fraction of a ticket bought, and we can't have a fraction of an attendee, right? 1.5 people can't attend. So the number of tickets must be whole numbers, and the number of people must be whole numbers. So I forgot to say that. The number of, sorry, not people, the number of events. So the number of tickets and the number of events must be whole numbers. Okay, how are the graphs alike and how are they different? Well, one way they're alike is they both represent discrete functions. That's why we had those dots, because we can't have in our domain fractions. And they're both increasing, right? They both went up. How are they different? Well, points on a linear function lie on a line. So our first function, the price for the tickets, went on a straight line. However, the points on the exponential function, the fact that the attendees, the number of people who attended, that lied on a curve. So an exponential function is still going to make a curve, while a linear function makes a line. Okay. What was the attendance at the initial seminar? 3 people. And then how did that change over time? Well, it doubled each time. The ratio was 2 to 1. There were 2 people came the next time for every 1 that was there the previous time. So what happened? The attendance doubled each year. Okay. So, as I said before, what happens is when you've got the same output, successive output values, and they're multiplying each time, and they could multiply by fractions, you need to know that. They have a constant ratio for each increase. And an exponential function can be represented by this. F of x equals ab to the power of x. X has to be a real number. A can't be 0 because that would make this pointless, right? B has to be greater than 0 or it's going to be really weird. And B has to be not equal to 1 because 1 to the power of anything is still going to be 1. So that's not going to change anything. Okay? The constant ratio is that B in our function. Oops, haha, slightly off sync. Okay, if it has inputs that are equally spaced integers, then the outputs are a sequence of numbers called a geometric sequence. You learned about arithmetic sequences before, where you were merely adding or subtracting a certain amount. Well, now you're multiplying by a certain amount, whether that's a whole number or a fraction. You're multiplying by a certain amount, and that makes it a geometric sequence. And of course, when evaluating, your exponents come up. Exponents aren't going away, right? So if we look at this table, any non-zero number raised to the 0 power is going to be 1. So c to the power of 0 is going to be 1 as long as c isn't 0. For example, 12 to the power of 0 is 1. Any non-zero number raised to a negative power, this is what trips people up, is that's equal to 1 divided by the number raised to the opposite power. So when we had c to the power of negative n, we just turned it into its reciprocal, 1 over c to the power of n. Again, as long as c isn't 0. So for example, 2 to the power of negative 3, we just make this its reciprocal. That's equal to 1 over 2 to the power of 3 equals 1/8. Okay, so here's an example here. We're going to make the table for this function, f of x equals 2 times 2/3 x. Remember, this is a b to the power of x. For the domain, and it gives us a domain here. And then we're going to graph it. So first we're going to complete it to calculate for an input of negative 2. So we're going to use that function with an input of negative 2. Well, what do we have? And I'm going to show it to you this way, and then I'm going to show it to you the way that I would prefer to calculate it. You can pick what works for you. So we have 2 times 2/3 to the power of negative 2. That's the same as 2 times 1 over 2/3 to the power of 2. So we made it its reciprocal and to the power of its opposite, which is equal to 2 times 1 over 4/9, which is equal to 2 times 9/4, which is equal to 9/2. Okay, here's the way I would have solved this. 2 times 2 to the power of 3, 2 times 2/3 to the power of negative 2. This is the same as 2 times 2 to the power of negative 2 over 3 to the power of negative 2, yes? So now I'm going to make each its reciprocal. I'm going to move 2 to the 2 squared in the denominator. 3 squared is going to go in the numerator. So I've got 2 times 3 squared over 2 squared, and then I can solve from there. 2 times 9 over 4, which is equal to, again, 9/2. Same answer, just a different way to get there. Figure out what works best for you. All right, so we can complete the table. We have an input of negative 2. F of x is 9/2. That means we'll have a point of negative 2, 9/2. Let's figure out if we have an input of negative 1. What are we going to do? Figure out either way. Here's the way I figured it out. Rewrite that with their reciprocals. I could have 3 to the power of 1 over 2 to the power of 1, but that's kind of pointless, right? There we go. So my output is 3, and my point is negative 1, 3. Go ahead and pause, fill out the rest of the table. Okay, here we go. There's what I got. If you got anything different, I suggest you pause and try to find your error. All right, and now we're going to go ahead and graph the function. First, I'm going to put on my scale. That was a weird way to say that. Identify my scale. And then I'm going to plot my points. Negative 2 comma 9 halves is 2 comma negative 2 4 halves, 4 and a half. Negative 1 3, that was easy. 0 2, another easy one. 1 4/3. 2 8/9, gets a little weird. And 3 16/27. That's about 3 comma about 1 half. Okay, and you can see the pattern here. We're getting a curve here, right? But remember, because we were given a domain with specific points, this is still a discrete function, so we're not going to combine those with a curve. And notice each one went up by what? It went up by, well, it went down actually, but we multiplied by 2/3 each time. So remember that terminology of the constant ratio? Well, that constant ratio is 2/3. Look at that, what we multiply by each time, 2/3. All right, I'll give you a moment to pause and fill this out, reflect on your own before you play. Okay, to identify the values of a and b, well, remember, the function is f of x equals ab to the power of x. So we have a equals 2, right? There's a is 2, and b equals 2/3. Okay, how is the value of the function changing as x increases? Well, it's actually decreasing as x increases. And you saw that, right? The graph was going, it's curving down. So as your exponent got bigger, your function, your output actually got smaller. Well, we're going to answer why that happened with these. So when b is between 0 and 1, what's happening? That number right there that we're multiplying by each time is between 0 and 1. And when you multiply a number by a fraction between 0 and 1, the product is less than the original number, right? 3 times 1/2 is 1 1/2. The number goes down. And when you keep doing that, then the results get even smaller, smaller and smaller and smaller. On the flip side, if b is greater than 1, and as long as a is greater than 0, then the function is actually going to increase each time, right? Because when you multiply by a number a by a number b greater than 1, so if a was 5 and we multiplied by 3, we'd get a bigger number, right? The product would be bigger. So the product will be greater than the number a. And if we keep doing that, then the results keep increasing further and further and further. So if b is a fraction less than 1 but greater than 0, your function is going to be decreasing. But if b is greater than 1, and as long as a is greater than 0, your function is going to be increasing. All right. Okay, today's a long video if you haven't noticed that already. We may or may not get this in one class, so if you're absent watching the video, you may find out that when you come back, you're actually ahead instead of behind. Okay, shut up, Decker, and keep going. All right, so you can actually write an equation as long as you can identify the values of a and b. The value of a is the value at function where x is 0. Well, because if you think about it, if f of 0 equals a times b to the power of 0, well, that means that it's a times 1, which just gives us a. The value of b is the factor that's the ratio of successive function values. So what is being multiplied each time? Okay, what is being multiplied by each time? So if we have f of x equals a times b to the power of x, well, now here's a question. What is x? That's how many times it's been multiplied by b, right? B to the power of 0 means it hasn't been multiplied by b at all. That's why it's just a. B to the power of 1 means it's being multiplied by b once, and so on. Okay, so let's write an equation from a verbal description. So we start with a piece of paper and we fold it in half. The total thickness doubles. Duh. Suppose an unfolded piece of paper is 0.1 millimeters thick. We're going to write an equation for the total thickness t as a function of the number of folds n. So we're going to have t of n, thickness of folds. Okay, the value of a is the thickness before any folds are made, or 0.1 millimeters. Because the thickness doubles with each fold, the value of b is 2. It doubles. So if we write the equation, we'll have t of n equals, well, our initial value, 0.1, times what happens to it, what we multiply by each time, 2 to the power of n. Why is the exponential function here discrete? Can you fold a paper like 1.5 times? No. You can only fold a whole number of times. And I think that whole number is actually 8. I don't think you can... Okay, shut up and keep teaching, Decker. All right, if the paper were twice as thick to begin with, what would be the equation? Well, our initial value then would be 0.2. So our function would be t of n equals 0.2 times 2 to the power of n. Not a big change, we just changed our initial value. Okay, question for you. Is this function increasing or decreasing? Bum, 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 bum. What is b? B is greater than 1, so it is increasing. The thickness of the paper will get bigger each time we fold it. All right, example 2, we're going to write an equation from an input-output pair, or from a pair of pairs, actually. So we dropped a ball, and on its first bounce, so after it bounced, hit the ground once, it reached a height of 15 inches. On the second bounce, it reached a height of 7.5 inches, and we're going to write an equation. So to figure this out, we're going to divide the successive values. So in fancy terms, we're going to divide the height of the second bounce by the height of the first bounce. So we're going to divide 7.5 by 15. And when we do that, we will get 0.5. So the value of b is 0.5. Each time it bounces, it only comes up half as high. Use your value for b and a known ordered pair to find the value of a. So here's our general form that we start with, kind of like the parent function, except not really. And then we're going to substitute the value for b. Since we know b, we were able to solve for b, 0.5. So h of n equals a times 0.5 to the power of n. And now we're going to substitute the input and output values for the first bounce, because that's what it told us to do. It actually doesn't matter which bounce, but we're going to use the first bounce. So for the first bounce, we had h of 0. We ended up with 15 inches, right? Equals a times b to the power of n. Oh, to the power of what? The first bounce? To the power of 1. And then we just need to simplify. So 15 equals 0.5a, because 0.5 to the power of 1 is 0.5. And then we can just solve for a, divide both sides by a half, and we get a is 30. Woohoo! We have a, we have b, we have everything we need for our function. So we have h of, oh, well, remember our function is f of x equals a b to the power of x. So h of n equals, what was a? 30, times, what was b? 0.5 to the power of n. There's our equation. Once again, is this increasing or decreasing? Look at b. Right, it is decreasing. You can logic it out by going, well, the ball's not going to bounce higher, but you can also say, well, b is a half, It's a fraction between 0 and 1. That means the function is decreasing. Okay, we are almost there. No, maybe. Whatever. We'll keep going. Okay, unit analysis to explain why b is a unit-free or unit-less factor. It's a weird way to think about this. Basically what we're saying is, well, when we figured out what b is, we had 7.5 inches divided by 15 inches, right? So our inches canceled, and we just ended up with 7.5 over 1 point over 15, or 1/2, or 0.5. There's no unit on this. So the inches divided out, leaving just the factor. Go ahead and pause and try the rest of these on your own. Oh, you gave up easily. Okay, I'm just teasing. Show that using the values for the second bounce will give you the same result. Remember how we plugged in the values of the first bounce? Well, we can do the same thing with the second bounce. What was the second bounce? That was, on the second bounce, it went up 7.5, right? So if we plug in 2 and 7.5, our function is going to look like 7.5 equals a times 0.5 to the power of 2, right? There's our output, our y. There's our input, that power of 2. And what does that give us? 7.5 equals 0.25a. And if we divide both sides by 1/4, we end up with 30 equals a. There we go. A is still 30 no matter what known point we use. A is going to give us 30. What was the initial height? 30, because that's what a is. And what was the height for the fifth bounce? Well, it's about 1 inch, and here's why. Well, if we plug in 5 for n, we get h of 5 equals 30 times 0.5 to the power of 5. And if we do the math on that, we're going to end up with 0.9375 inches, which is about 1 inch. Okay. What is the ratio of the height of the fifth bounce to the initial height? So if we use that real number that we had, 0.9375 over 30, that's our ratio. How is this related to the constant ratio for the exponential function? Well, so if we divide this out, we end up with 0.0315. And how is that related? The ratio is equal to the fifth power of the constant ratio, or 0.5 to the power of 5. So this number right here, which is a result of this ratio, is 0.5 to the power of 5. Why did that happen? Well, some of you are going to say, because n is 5, and it's just going to happen. Or you can also say, well, the ratio of the height is 30 times 0.5 to the power of 5 over 30 times 0.5 to the power of 0. So this is the height after the first bounce, fifth bounce. This is the height before the first bounce, which reduces to 0.5 to the power of 5. Okay, number of ways of saying the exact same thing. Okay, yay, we did make it to the end. That was probably the longest video I've done all year. I will see you in class. I hope you were here for it. Otherwise, I'll see you in class.